In our introductory video on freezing damage in building materials, we saw one way in which freezing damage may develop in porous materials. This concerned the specific and extreme case whereby freezing proceeds from all sides, a situation we refer to as Case 1. We also saw how unsaturated pores may prevent water from being trapped and generating stresses as it crystallizes. In stones with coarse porosity, that is, with pores of 1 micron or larger, damage is only likely to occur if the pores are more than 91% full of water, so that there is no room to accommodate the expansion as water turns to ice. In this video, we expand our analysis to a more practice-relevant situation where the material freezes from one side. It is our case 2 and concerns hydraulic pressure. In most cases, freezing only proceeds from one side, as in the exterior walls of buildings. Under such circumstances, as ice grows into the material from the colder side, it pushes unfrozen water towards the warmer side. If the material is permeable enough, the pressure in the water is low. In such cases, the tensile stress felt by the material may remain below its tensile strength so that damage does not happen. However, if the water cannot flow freely enough as the ice advances, for example owing to hydrophobic treatments, blocked pores, or very small pore sizes, then hydraulic pressure builds up in the liquid, causing it to push out against the solid matrix so that damage becomes increasingly probable and cracking is expected when the tensile stress in the porous matrix exceeds the tensile strength of the material. To get a better grasp on this process, let us now derive a simple equation capturing the main features of hydraulic pressure. For this, we consider a cylindrical pore containing water and open at both ends. Therein, we represent an initially unfrozen pocket of water of length 2w. Should this pocket freeze, the ice formed would occupy a volume 9% larger. If only part of it freezes, then the frozen part will also be 9% larger than the portion of water that froze. Let us consider this process starting with the nucleation of an ice crystal in the center of the water pocket. As this crystal grows, it pushes the yet unfrozen water ahead along the pore. This causes frictional resistance between the water and the pore wall, which produces pressure in the liquid. Indeed, because of its viscosity, water partially resists being pushed through the porous network. To analyze this, let's first denote by 2x the crystal length at time t, and by 2x prime the combined length of that crystal and the remaining water. Let us then apply the Poiseuille relation, giving the flow rate dV over dt, which represents the volume V of liquid flowing per unit time through a cylindrical pipe. Poiseuille's relation states that dV over dt varies as the fourth power of the pipe radius r is proportional to the pressure gradient, expressed by the pressure drop delta P over the pipe length L, and is inversely proportional to the fluid viscosity eta. We can also express this flow rate Q, considering that the displaced volume of liquid dV on each side of the crystal is the product between the cross-sectional area A of the pipe and the rate at which water is displaced dx prime over dt, giving that Q is equal to A times dx prime over dt. The advancement of the waterfront, dx prime, can be written as the product between the extension of the crystal length dx and 1 minus the ratio between the densities of ice and water, where the density of water is 1 and the density of ice 0.917 gram per centimeter cube. Substituting into the flow rate equation and rearranging, we get that Q is A times 1 minus the ratio of ice to water densities times dx over dt, where dx over dt is the unidirectional growth rate of ice. Combining this with the Poiseuille equation and considering a circular cross-sectional pipe, for which A is pi r squared, we find that the pressure difference varies as the ratio of the pore length over the square of its radius r. This underlines that if water must be pushed forward over large distances and/or the pore size is small, then substantial pressures can build up and damage the porous material. A more detailed analysis of a realistic pore system retains the same essential features. The pressure increases linearly with L and is inversely proportional to the square of the mean pore size. This simple equation captures key differences in susceptibility to freezing of sedimentary stones and cementitious materials. Indeed, sedimentary stones are coarser than cementitious materials and therefore less at risk of developing important hydraulic pressures. If such stones are unsaturated, water may often flow to empty spaces fast enough to alleviate the pressure buildup. That is why such materials are most susceptible to damage when fully saturated and freezing from all sides, as may happen to fountains and finials exposed to rain. For cementitious materials, many of the pores are smaller than 100 nanometers in diameter, so they offer high resistance to flow. Therefore, an effective strategy to make such materials resistant to freeze-thaw cycles is to artificially entrain air voids when preparing them. This is done by using surfactants to create air voids 10 to 100 microns in diameter, surrounded by a thin shell of cementitious paste with a fine porosity. These air voids serve as sinks for water displaced by ice formed in the small pores of the cement paste. For frost protection, there should be a void within 200 microns of any ice crystal nucleating point to prevent destructive pore pressure. In essence, this distance is the length L in our equation, and keeping that length within a range of 200 microns prevents hydraulic pressure from producing tensile stresses in excess of the concrete's tensile strength. In practice, most situations for which the air void to air void distance, or spacing factor, is below 200 to 300 microns are considered safe. If the same amount or more air is entrained as larger but more distantly spaced voids, the situation would not be safe. It is therefore the spacing factor and not the total amount of air entrained that can protect cementitious materials from hydraulic pressure. In conclusion, porous materials can be damaged during the freezing of water in different ways. Volumetric expansion causes catastrophic damage if water is trapped in the pores, but this is an unusual situation in practice. A more probable situation is that of hydraulic pressure, which develops when water cannot flow away from the freezing front without building up too much pressure. This may be due to small pores or large saturated volumes. Such situations can lead to damage when freezing happens only from one side and is more critical for cementitious materials than sedimentary stones, because cementitious materials have much finer pores than sedimentary stones. As we shall see in a future video, frost damage in building stones is most likely to occur when a saturated stone is exposed to a gradient in temperature.